Hello and welcome to another video. In this video, I'll be talking about design for assembly. Now, design for assembly is a very important activity for design engineers, especially in the concept development phase when we are developing new types of concepts to solve problems. So when we are designing systems, we need to design with assembly in mind. So here is an example. Let's say if you are having a part like this, and if you are making multiple parts, 5 parts which are all assembling using multiple fasteners, then it makes the design overly complicated. What if we can combine all of these parts into one single component as shown on the right hand side and only have 4 fasteners? So we are basically reducing the number of parts, reducing the complexity of assembly, and reducing the chances of any error occurring during the assembly process. The activity of designing for assembly for design engineers, especially in the concept phase, when the conceptualization is happening, because that's when it is the most impactful. Designing with assembly in mind has 3 guiding principles. The first one is the most obvious one, which is to simplify the assembly. Not make it too overcomplicated, make it as simple as possible, and importantly, make it intuitive. Intuition is very powerful. We take the example of IKEA. IKEA is a brand which manufactures furniture which can be assembled by the user itself. So when the assembly has to be done by the user is not skilled at assembly. So the assembly should be intuitive. It should be easy for the user to do. Hence intuition and building that into the concept of the design, of the mechanical design, is a powerful way of making systems easy to assemble. The next important principle is reducing parts wherever possible. Now, when we are designing a concept, if we find that there are certain parts which can be reduced, there are 3 components which can be made into one, as in the earlier example, or 2 components into one, or whatever that may be, we should do that and reduce the number of parts possible. That increases the ease of assembly and also reduces the cost of assembly. Here are some examples which show these 2 principles at play. So here is an example of a block which is having a plate on top, which is assembled using a floating fastener and a fixed fastener. So the fixed fastener is assembled into the threaded portion on the base block, and the clearance hole is on the top plate. Over here there are 2 clearance holes, and is assembled using a nut. The bolt is assembled using a nut. Now what if we can modify this portion of the design? This portion, what if we can modify it and make it a tapped hole instead of having a floating fastener assembly? We can reduce this nut in terms of its numbers, and the design will be easier because it will be uniform. You will not have any confusion between this floating fastener and the fixed fastener. Both will be fixed fasteners. It will make it simpler, and the number of parts would have reduced. Here is another simpler example. So let's say, for example, there is a pipe over here, or say a frame on which this block has to be mounted using 3 separate brackets which are welded onto this frame. Instead of these 3 separate brackets, we can combine them into one. Although it will increase the weight slightly, but it will improve the assembly. It will make it much more easier. We can imagine that welding these 3 brackets separately will almost always not maintain the top level of the mounting surface. It will not be uniform, because when we are welding there will be variations, whereas over here it will have a uniform mounting surface. Hence the overall performance also will be improved, the precision will be better, and the assembly process is simpler, and overall cost is cheaper. The third principle in design for assembly, which builds on the first 2, is reducing the time to assemble. Now time is money in production. How much ever the time is required for an assembly process to take place, that much the cost will increase. For a complex assembly which has many parts, many sub-assembly processes, the time will be higher, and hence the cost implication will be higher. If we are able to reduce the time for an assembly to take place, we are eventually reducing the cost. So let's say if you have simplified the assembly, made it as intuitive as possible, and also reduced the number of parts, remove the redundant parts, the next step is to reduce the time to assemble. A very good example of this is the assembly of bolts blind assembly. So let's say, for example, if you're having a part like this is a cross-sectional view. This blue color part is assembled to this yellow color part through a bolt, and you're assembling from the top. You cannot see the bolt, but this clearance is very important for the manual assembly or manual insertion of the bolt inside the hole. If this clearance is not there, it will be very difficult for the bolt to be inserted inside this hole and tighten it. And also another important feature over here is this conical feature. If you are having a flat end bolt, then the time to locate the bolt inside the hole will be higher as compared to a conical feature. Hence, these small details will directly have an impact on the time to assembly. We want to reduce the time to assembly, and whatever the design changes we need to make, that has to be done at the initial phase. That is always better. So time to assemble is very important. Generally, the time required to assemble part goes in locating the part or aligning the part for assembly. Hence, if you are designing self-locating or self-aligning features in the components themselves, then this time to assemble can be reduced. So here is an example. Here is an example of a block which is having a rectangular cavity in the center, and a sheet metal part is positioned on top, and the central rectangular hole of the sheet metal part should align with the cavity on the block. So that is the requirement. Now if we are having an assembly like this, and this part is being welded over here, here and here, then a change in the design on the block like this, having a depression like this over here and over here, which basically locks the location of the sheet metal part inside that depression, it makes it easier for this part to be aligned and located. So this basically arrests the location of this green color part on this gray color block, and it is easier for it to be then welded or whatever the fastening process may be, because it is now located and perfectly aligned. So the first design requires proper location and alignment. It requires additional skill or requires an additional fixture if it is robotic assembly. Whereas in the second case, the feature on the design itself is self-locating or self-aligning. Hence, the time to assemble will be much lower on this. Another important concept in design for assembly is Poka-yoke or error proofing in design. So Poka-yoke is a Japanese word for error proofing. Let's say if you are having a part like this, and you see visibly we cannot make out that the size of the holes are different, but this hole is smaller than this. This is a slightly larger hole. Now to make sure that in assembly it is not assembled the wrong way, we need to add some features for error proofing the design. So adding a feature like this cutout will basically say that the largest hole is this hole over here, which is near to the cutout. So this is called Poka-yoke. Here is another example of Poka-yoke in design. So here is a plate which is having 3 holes, 2 are small and 1 is big. So this plate can be assembled the other way also by orienting it in by just rotating 180 degrees. The location of this hole will come over here, but that is wrong assembly. We do not want that assembly to take place. So to avoid that, we can have a notch like this, which makes it difficult to rotate that part and assemble it, because of this notch it will not basically match the mounting surface on the purple color part. So this is another example of using Poka-yoke design features for error proofing the design.